Alpha particles are larger than beta particles. They can be stopped by a simple sheet of paper, while beta particles require a thin sheet of aluminum or a material such as plexiglass to stop them. Beta plus particles indicate an excess number of protons in the nucleus, where a proton is then converted into a neutron, resulting in a beta plus particle, which is commonly called a positron. The positron is essentially similar to an electron, but carries a positive electrical charge and is accompanied by a neutrino particle, unlike the beta minus particles, which produce a beta minus particle and an antineutrino. What essentially happens is that the proton transforms into a neutron particle, which reduces the atomic number by 1. However, there is no change in the mass number because this reduction in protons is balanced by an increase in the number of neutron particles, so the mass number remains the same. So the positron that was formed is... So where does the beta minus go? After that, the beta minus starts interacting with the existing tissues, losing energy and causing DNA damage or mutations, whether repaired or unrepaired, and contributes to cell degeneration or any type of repair that might occur. As for the beta plus, when it first emerges, or the positron, this is the concept behind FDG or PET-CT imaging. The positron that comes from the fluorine atom present in fluorodeoxyglucose, FDG, begins to undergo a collision, meaning it interacts with an electron that is naturally present in the surrounding medium. It is expected to encounter electrons because there are atoms within a few millimeters, and something called This is a diagram illustrating something called annihilation. Annihilation means that two gamma photons are emitted at 180 degrees to each other, and each of them carries an energy of 511 kilo-electron volts. This energy represents the mass of the electron and the positron. Here is the annihilation site, or the location where the annihilation occurs, as the positron moves. When a positron encounters an electron in the medium, they produce two gamma photons. Each of these follows the great equation of Einstein, which states that mass is converted into energy. At this point, the energy you have represents the mass of the electron or the mass of the positron. So, these two masses have been converted into energy. There is a phenomenon that competes or interacts a bit with the positron or beta plus, which is called electron capture. What is this? Electron capture about? The topic of electron capture is that you have an excess number of protons. There are many protons, which increases the positivity charge of the nucleus. Consequently, when the positivity charge of the nucleus increases, it can create an attraction for the electron that is in the nearest electron shell, pulling it closer until it is attracted to it. This electron combines or collides with a proton inside the nucleus and transforms into a neutron. This is what I call electron capture, and it occurs in iodine-123. That's a radioactive isotope. 333-3. So gamma radiation is emitted, and X-rays are also produced. Now, the X-ray that was emitted is a result of electron capture. That's why someone might ask you, Is the characteristic X-ray followed by electron capture? Yes or no? The characteristic X-ray followed by electron capture. Why? Because the simple area is that I have here is my nucleus. And here is the postulate where there is an excess number of protons. This positive charge has increased significantly, which enhances the attraction force for the electron present here. As a result, this electron will experience attraction and combine with a proton that is present here. The electron transforms into a neutron. And since the electron has left, there is a vacancy, prompting an electron from a higher shell, specifically the L shell, to drop down to fill the gap in the K shell. This process results in the release of energy in the form of X-rays, specifically characteristic X-rays, which I refer to as characteristic because, as we will explain later in the chapter on X-ray imaging, it represents the difference in binding energies between two energy levels. The energy of this characteristic X-ray is 228 keV. Therefore, when they examine iodine 123, they find that there are characteristic X-rays being emitted along with the gamma radiation that is emitted from the atom itself. So, this is electron capture, which always occurs with heavy atomic numbers or large atomic numbers, and there is competition between it and beta plus. Can it happen at the same time? Can both reactions occur simultaneously? Doctor. Yes, it can happen, doctor. It can happen with certain probabilities depending on the atom itself. Both can occur at the same time with the atom, but as I mentioned, it depends on the atomic number. The larger the atomic number, the greater the probability of electron capture occurring. All right, doctor. All right, I sincerely hope that the ongoing discussion isn't becoming tedious or boring for anyone, and that each of you is fully focused and engaged with me at this moment. I mean, do we have any medical professionals like doctors or nurses with us in this session? Or do we perhaps need to take a short break to refresh ourselves? Let's consider a 10-minute break if necessary. Shall we take 10 minutes and come back again? Yes, there is no problem. We will take 10 minutes and come back again. For example, I don't know what time it is for you, but let's say it's about 10 minutes and then we can come back, okay? All right?
قليل قليل.
Well, let's continue our discussion about electromagnetic waves. This is the last part that includes some basic science. Perhaps this section has a bit of information that is somewhat limited, but I believe this is one of the important things or basic concepts that will be built upon in the basics of medical imaging for the rest of the course, God willing. Electromagnetic waves are all around us. For example, you can use a laptop, a mobile phone, or the visible light around us. All of this falls under electromagnetic waves. However, you can use a mobile phone for long periods without feeling any issues, and you can use a laptop for long periods without feeling any problems. You can also listen to the radio for long periods without feeling any issues. But you cannot enter an X-ray machine or be exposed to a radio isotope that emits a type of radiation, whether it's a gamma ray or specifically gamma radiation, because beta and alpha radiation will stop at a short distance. You cannot be exposed to these types of radiation for long periods. Why? Because, simply put, it depends on the energy of the radiation. The energy of radiation from X-ray or from gamma ray or from the different types of radiation varies. The difference between the various types of radiation is a difference in energy, a difference in the frequency of the electromagnetic waves. Electromagnetic radiation refers to, when I say electro and magnetic, I mean it consists of electric and magnetic fields that are perpendicular to each other, and at the same time they are perpendicular to the propagation direction of these waves. Now, electromagnetic radiation or electromagnetic waves have certain properties, such as the sine wave shape. It has an amplitude of a certain height, a wavelength, and a frequency. When I say amplitude, I mean the height of the peak. When I say wavelength, I refer to the distance between two peaks or two bottoms. When I say frequency, I mean the number of cycles. For example, if I start here from 0 and this is the first wave, I return to 0 and then repeat my wave again. So I have many cycles. The number of cycles per second expresses the frequency for me. The higher the frequency, the higher the energy of these waves. You find that X-ray and gamma ray have high energy or frequency. While its wavelength is small, there is an inverse relationship between energy, wavelength, and frequency. Meanwhile, there is a direct relationship between energy and frequency. This distinguishes radio waves from microwaves. Even the MRI, magnetic resonance imaging device we have in terms of energy, is related to X-ray. The energy of X-ray has a large frequency and a small wavelength. The issue with this energy is not in its value, but rather in its effect. There is information that the lethal dose of radiation is about 4 gray, which converts to approximately 69 kilocalories. When they converted this lethal dose to kilocalories, they found that the 69 kilocalories you actually get from just one sip of coffee. So the small amount of coffee you drink contains the same calories as the lethal dose of radiation. The whole story is not about radiation itself. The idea is all about the effect. As we will discuss later, it relates to the biological effects of radiation. In fact, the MRI device specifically uses magnetic fields and radio waves to create detailed images of the organs and tissues within the body. Moreover, it is important to understand that the energy levels involved in MRI are significantly different from those in X-ray radiation. Furthermore, the biological effects of radiation are a complex topic that requires careful consideration and understanding. You will see the interaction mechanism and what happens with the cells, which stimulates apoptosis, as I mentioned, the strength of the field itself, or the strength of the magnetic field, the wavelength, and the distance between two successive peaks. Nevertheless, we can identify the receiver among the existing components. The unit of time is measured in seconds, which is referred to as the period of the wave. It indicates how long it takes to complete one cycle, which is the number of peaks passing a point in 1 second. This means the number of peaks that can pass, or the number of cycles that can occur. The unit for this is hertz, or cycles per second. Velocity is always distance over time, meaning the distance traveled by the peak in 1 second. This is the concept of velocity. When we talk about the energy of electromagnetic radiation from the equation of the Planck equations, energy is equal to the Planck constant multiplied by frequency. This frequency is the same as the speed of light divided by the wavelength. The Planck constant is the energy equivalent of the Planck constant in frequency, which is the same as the wavelength. In this context, energy is photon energy, h is the Planck constant, and f is the frequency. There are some definitions or things that we need from you, as you mentioned, you want to know, such as the inverse proportionality between frequency and wavelength, as well as the inverse proportionality between energy and wavelength, and the proportionality between energy and frequency. For example, regarding the movement of radio waves, their wavelengths range from 30 to 6 meters, the frequency ranges from 10 to 50 megahertz, and the energy ranges from 40 to 200 nano-electron volts. Electron volt is the unit for this. And 50 megahertz from yours. The higher your energy value is, such as in the cases of X-ray and gamma-ray radiation, the further and faster it can travel through different mediums. This is because these types of radiation possess high energy levels that allow them to penetrate materials more effectively than other forms of radiation. For instance, X-rays are commonly used in medical imaging to see inside the human body without invasive surgery, while gamma rays are used in cancer treatment to target and destroy cancerous cells. When comparing different types of radiation, you will find that the wavelength is larger here, meaning that the distance between successive peaks of the wave is greater. This characteristic affects how the radiation interacts with matter and can influence its applications in various fields. For example, longer wavelengths are typically associated with lower energy radiation, such as radio waves, which are used for communication purposes. In contrast, shorter wavelengths, like those of X-rays and gamma rays, are associated with higher energy and are used in more specialized applications. Understanding these differences is crucial for effectively utilizing radiation in technology and medicine. While the wavelengths here in X-ray and geometry are small, the frequency increases with the increase in energy, and at the same time, it increases with the decrease in wavelengths because, as I mentioned, there is an inverse proportionality between frequency and wavelength and a direct proportionality between frequency and energy. Now, there is a very important law that expresses the inverse square law, which states that intensity has a relationship with distance. What does this mean? It means, for example, if you are currently 1 meter away from an X-ray tube, you are exposed to a certain intensity. If you double that distance to 2 meters, the intensity decreases to a quarter. Why does it decrease to a quarter? Reducing the robot involves inverse proportionality between the intensity of radiation and the square distance, which is the inverse square law. This makes sense. But there are some definitions we need to clarify, such as photon fluence, energy fluence rate, and energy flow rate. What do these terms mean? If today I have an X-ray tube and I look at the exposed area, while I am close to the X-ray tube, I will find that it represents this square. This makes sense because when I am close to the X-ray tube, the exposed area is small. But when I move away from the X-ray tube, this exposed area will indeed increase, right? The further I move away, the more divergence occurs in the beam, so the area that is exposed will appear larger to you. Now, did the number of photons change? Did the number of X-ray photons emitted from the X-ray tube change from square number 1 to area number 2 to area number 3? Or is the number of photons in that one square the same as the number of photons in all 4 squares? No, of course, the number of photons remains the same. There has been no change. In the whole area, when comparing 1 square to 4 squares and 9 squares, the total number of photons remains the same. However, when I compare 1 square to 1 square to 1 square, I find that the number of photons in this square is greater than the number of photons in that square because it was divided by 4 here and by 9 there. So the number of photons here has decreased significantly. Therefore, what happened is that the concentration of the number of photons decreased. This is what happens. You have the number of photons as a whole area that does not change, but in the individual square, it has decreased. So the intensity of radiation in that single square will decrease. But when I say the number of photons present at a certain area, what do I call this? The photons. In a specific area, and to understand this, it means that it is emitted in a way that affects the area. After that, it affects the area with the number of photons or the... What exactly is it? At a specific and certain time, this particular beam of light is referred to as OK. If I have these photons, it includes the total amount of energy. The amount of energy captured by the photons is collected all together over a certain time, in a specific area at a certain location, which I call energy fluence. Therefore, the summation of all the photon captures present at a specific time in a certain area is referred to as energy fluence. The number of photons present at a specific time in a certain area is called photon fluence. Now, what about energy fluence rate? It is like when you compare here to there to see what happens to that square rate. It decreases. Yeah, I am comparing the energy fluence rate, or what happens to the intensity of radiation when it decreases, is referred to as the energy fluence rate. So, the number of photons per unit area at a given time corresponds to the photon fluence. The total amount of energy from different photons along with the cross-section of the beam per unit area is called energy fluence. Photon fluence. Photon fluence. A beautiful collection of photons, and a beautiful collection of photons, and a beautiful collection of photons, and a collection. The total energy per unit area passing through the cross-section per unit of time is measured in watts per millimeter square. This represents the total energy per second of photons in area A or B, which I refer to as the energy flowing state. There is a change occurring in the strength of the beam in this area or location over time, or with distance from the X-ray source. So I will always find that when I was here, the exposed area increases as the distance from the source increases, indicating a direct proportionality between the area and the distance. The further away you are, the larger your area becomes. This is clear. There is a direct proportionality between the area and the square of the distance. As we discussed, there is an inverse proportionality between the intensity of radiation and the area, because as one increases, the other decreases. You will stay away from the area, and the area will increase while the area will decrease as we mentioned in each square. Therefore, the law appears to me that the area interacts with the area. However, the area is not easy to measure. Well, the energy fluence, or the intensity of radiation, that's why I encountered a term called air Kerma. Air Kerma, which is the kinetic energy released per unit of mass, makes it easier to measure with radiation measurement devices or radiation instruments. It's easier to measure than energy fluence or intensity of radiation. So, what is air Kerma? Simply put, air Kerma refers to the interaction of radiation with air molecules, causing ionization.